Good afternoon, welcome to btosacademy, welcome to my maths class. Today I am going to start new topic or new chapter, trigonometric inverse function. Already I have used sin inverse x, cos inverse x, tan inverse x in different topics, in case of complex number, also in case of differentiation, though I have not discussed about the matter of inverse trigonometric function. Only we have used the results. Now I am going to start this important chapter, trigonometric inverse functions or inverse trigonometric functions. First of all, let me remind you, my students, learner, already in the last few episodes I have discussed relations and functions, and after learning those topics we have gained the idea of inverse function. If f be a function from set x to set y, where x and y are non-null sets, such that f is 1 and 1 and onto, or injective and surjective, then we say the function f is bijective. And in case of bijective function for say f, what we find that for every small x in set x, we get small y in set y. Let me represent that with the help of diagram. Elements of set x are x1, x2, x3, x4, and elements of set y are say y1, y2, y3 and y4. If f is 1 and onto, then we have learned that for every small x here, x1, x2, x3, x4, etc., we have distinct y's. For x1 here, y1, for x2, y2, for x3, y3, for x4, y4. Here, for distinct member of set x, we get distinct y of set y under the function f. Then f is 1 and onto. Then f is bijective, and in case of bijective we consider inverse function denoted by the symbol f inverse, which associates every y of set y to a distinct x in set x, denoted by the symbol thus. These are the preliminaries of inverse function. Now, in case of bijective function, we define inverse function given by this. Now, in case of trigonometric function, we have seen that in general trigonometric functions sine function, cos function, tan functions, etc. are not invertible in the domain, and the domain in general set of reals. Actually trigonometric functions are periodic functions. Now if we can break or split those periods into suitable intervals or subdomains, then we can easily discuss the invertibility of those functions. Let me first write the domains and range of trigonometric functions. Sine function, already you know, from set of reals to the closed interval, this one, then cosine function, set of reals to closed interval -1, 1, same, and for tan function, set of reals to set of reals except already you know tan pi by 2, undefined, tan 3 pi by 2, tan of minus pi by 2, etc. That is why the range will be set of reals minus set of x such that x equal to 2n plus 1 into pi by 2. That means odd multiple of pi by 2. Then for cosec, set of reals to range is this one, then sec set of reals to set of real minus set of x such that x equal to 2n plus 1 into pi by 2. Sorry, the domain is this one, cosec, domain is this one minus this. In case of cosec, domain is this one and range is In case of sec, domain is this one and range is set of reals minus sine, cos, tan, cosec, sec, then we have cot. For cot, domain is R minus x such that x is equal to n pi to set of reals. For tan function, domain will be R minus set of x such that x is equal to 2n plus 1 pi by 2 where n is set of integers and range is set of reals. We say minus infinity to infinity, and for cosec function, domain is set of reals minus set of x such that x is equal to n pi n belongs to set of integers 2 range is set of reals except the interval minus 1 1. This is for cosec function. Then for sec function, set of reals minus set of x such that x equal to 2n plus 1 into pi by 2 already mentioned n set of integers 2 set of reals minus the interval minus 1 1. Actually, you know that in case of cosec sec, the value of cosec theta or sec theta will be either greater than or equal to 1 or less than or equal to minus 1. That is why this symbol have been used. And for cot function, domain will be R minus set of x such that x equal to n pi, that is same as that of cosec. N is set of integers 2 set of sec cot. Sec this, sec this, and cot set of reals. In case of cot function, already you have learned the value of cot theta will be any real value. Thus, I have made the chart. It will be better you practice and apply the general knowledge for remembering the domain and range for these 6 trigonometric functions. Then I will make the chart for the inverse trigonometric functions. Before making that chart, I mentioned that in case of sine function, in case of sine function, inverse is denoted by the symbol sine inverse x. Actually, considering the domain, and that domain is not the general real, set of real rather. In case of sine function, if we impose the restriction so that sine function will be invertible. Already I have mentioned earlier, in general, all trigonometric functions are not 1, 1 or onto. That is not bisective. But if we impose some restrictions on the domain and also range, then each of these 6 trigonometric functions will be 1, 1 and onto in that specific domain and range, so that in that specific domain and range, each of these functions will be invertible. Considering those restrictions on the domains and ranges, we apply the idea of sine inverse, cos inverse, tan inverse, sec inverse, cosec inverse and cot inverse. Already it is discussed earlier, if a function be 1, 1 and onto, or in short we can say bisective function, for given domain and range, then we can apply, or we apply the sense of inverse function, that is the reverse matter, and inverse of f is denoted by f inverse. And in case of trigonometric function, in case of sine function, we denote its inverse by sine inverse x, and for cos we apply, or we use the notation cos inverse x. For tan function we apply tan inverse x, etc. Now the next matter is that we have to discuss the domains and ranges in which different trigonometric function will be invertible. Before making that chart, let me give you some tricks for remembering these things. For sine function, already you have learned -1 less than equal to sine theta less than equal to 1. For cos theta also, -1 less than equal to cos theta less than equal to 1. For tan function, minus infinity less than tan theta less than infinity. And for cosec theta, greater than equal to 1, or cosec theta less than equal to -1. And for sec theta also, sec theta greater than equal to 1, or sec theta less than equal to -1. And for cot theta, this is also minus infinity already you have learned earlier. That is why to memorize, follow these results and then try to remember these things. Domain in case of sine function, set of reals, and value is within -1 and 1, that is represented by this symbol. This is inequality type symbol, and here it is represented by interval symbol, etc. Now I am going to make the chart for the trigonometric inverse functions. This will be number 4 actually. First of all, function, then domain, and range. I write serially: sine inverse x, cos inverse x, tan inverse x, then cosec inverse x, sec inverse x, and cot inverse x. Number 1, number 2, number 3, number 4, number 5, number 6. Domain, and range is -π/2 to π/2. I shall discuss later on about this. First I make this table: -1 to 1, and it is 0 to pi. In case of tan inverse, set of reals, and this is -π/2 to π/2. For cosec inverse are set of reals minus the set -1 to 1, and range will be -π/2 2 pi by 2 except set of 0. Then for sec inverse, domain is same, domain is set of reals minus the closed interval minus 1 to 1, and range is 0 to pi except set of pi by 2. And for cot inverse x, domain is set of reals and it is range is 0 to pi. Here I have written domain and range. Actually, I have mentioned earlier, in general, trigonometric functions are not one on two. In the general domain, that is set of reals, if we impose the condition restriction or condition on the domains and range, actually to understand that, we have to draw the graph of different trigonometric functions. Just I am drawing here sine function. This point is pi by 2, 0. This point, and this point is pi, 0. And this point pi by 2, 1. You see, this is the sine curve. And this point is minus pi by 2, 0. This point is minus pi by 2, minus 1. Thus, you note this interval, in the interval minus pi by 2 to pi by 2. That means this part of the curve I have overdrawn. This part, in this part, the sine function is 1 and on 2. You see, this is increasing 1. Starting from here up to this, the curve is increasing. Value of sin x is increasing. Therefore, if we consider this interval, Actually, we have to take the closed interval. In this interval, sine function is bisective. Least value is -1, greatest value is 1. Now we can split the whole interval into such sub-intervals, in each of which sine function will be 1, 1 and on 2. That means invertible. Now this interval is taken as principal value interval, principal value domain, principal value interval, and in that case range will be -1 to 1. Now keeping this idea, we take this as principal, as per the graph, this part is taken to be principal value branch, and we can also discuss for other trigonometric functions principal value branches are these. I have written down in this table. Now keeping this idea, this knowledge, we shall improve the matter. Next one, here I have mentioned principal value. For principal value branch, domain is this and range is this one. Now you can read yourself from your textbook the principal value branch. For the principal value branch for each of these inverse trigonometric functions, domain already written in this chart, and the range. Next, I move to different properties, also you may call formula. Y equal to sin x. Keeping all the restrictions in our mind, we just simply learn these things. For the value, certain value of say x, sin x is equal to y. Then under different restrictions I have discussed earlier, we can say inverse trigonometric function for this will be x equal to sin inverse y, and already you have learned that now x equal to sin inverse y. If I replace this one here, what we get? Sine of sin inverse y is equal to y. Again, y is sin x, therefore if I put this value here, also sin inverse sin x equal to x. Remember this thing, I have already discussed, we have split the whole real set, that is domain, into different smaller intervals in which the function is invertible, that is 1 1 and on 2. Keeping all these things in our mind, we can now improve our idea and progress. Therefore, we have got two properties. First, sin of sin inverse y equal to y. If we replace y by x, then that will be sin of sin inverse x equal to x, and sin inverse of sin x equal to x. Similarly, we can write for cosine function cos of cos inverse x equal to x, cos inverse cos x equal to x, tan of tan inverse x equal to x, tan inverse tan x equal to x. If you are asked to prove, then you follow this method, or let me prove one. For this one, let cos inverse x equal to theta. Therefore, x equal to cos theta. Now, here I can replace this one. Cos theta means cos inverse x. Finally, what we have got? Cos of cos inverse x equal to x. Then for this one, cos inverse, if I say this one as 1 from 1, cos inverse x equal to cos theta. Therefore, cos inverse of cos theta equal to theta. Now, if I write x in place of theta, then cos inverse of cos x will be. We can prove similarly other inverse trigonometric functions, cosec inverse, sec inverse, tan inverse, etc. etc. Then I must mention here the domains, etc. For sine inverse, for sine inverse of sine x, here and for cos inverse of cos x, here x belongs to 0 to pi, 0 to pi, and for tan inverse x will be set of reals. Tan inverse tan x minus pi by 2 to pi by 2. Minus pi by 2 to pi by 2. Actually, to remember these things, you must practice a lot. But in case of solving sums, generally we have to use different formula. Now we move to the next set. I call set. Cosec inverse x, that is equal to sine inverse 1 by x. Let us prove this one. Let cosec inverse x equal to say theta. Remember one thing, inverse of different trigonometric functions are angle. That is why I usually take theta. Therefore, cosec theta equal to x. Now we know cosec theta is nothing but 1 by sine theta. Therefore, sine theta equal to 1 by cosec theta, that is 1 by x. Therefore, theta equal to sine inverse 1 by x, and already I have taken cosec inverse x equal to theta. Therefore, cosec inverse x equal to sine inverse 1 by x. And since x is at the denominator, therefore that cannot be 0. Actually, the restriction here is mod x greater than equal to 1. And similarly, we can show sec inverse x equal to cos inverse 1 by x, along with the restriction mod x greater than equal to 1. Then number 3, cot inverse x equal to tan inverse 1 by x, where x is positive. One thing I must mention here, that don't think sin inverse x is never equal to sin x to the power minus 1. Don't be confused. Sin inverse x never equal to sin x whole to the power minus 1. Actually, sin x whole to the power minus 1 is equal to 1 by sin x. Hence, don't be confused. Sin inverse x, that is not equal to sin x whole to the power minus 1. Actually, sin inverse x is an angle. Then I move to the next set. I call it number 8. Sin inverse minus x, that is equal to minus sin inverse x. Let me prove that. Let sin inverse of minus x is equal to theta. Therefore, sin theta equal to minus x or minus sin theta equal to x. Now we know sin of minus theta is minus sin theta, therefore this is equal to x. Therefore, minus theta is equal to sin inverse x minus theta equal to sin inverse x, therefore theta equal to minus sin inverse x and theta equal to this one. And don't be confused about the domain. Here x is of course next. We have the second one. I write here as corollary cosec inverse of minus x. Cosec inverse of minus x is equal to minus cosec inverse x. Here mod x greater than equal to 1. You can prove yourself, and it is better you prove yourself. I will show few and you will work out yourself. Then I call number 2 cos inverse of minus x is equal to pi minus cos inverse x. Here x is also let us put this. Let cos inverse of minus x equal to theta. Therefore, cos theta equal to minus x. From that, minus cos theta equal to x. And we know cosine is negative if we consider the principal value branch, or just simply principal value, then negative in second quadrant cos of pi minus theta equal to x. Therefore, pi minus theta equal to cos inverse x. From that, theta equal to pi minus cos inverse x, that is cos inverse of minus x is equal to pi minus cos inverse x. See that cos theta equal to minus x, I can take that negative sign on the left, that is minus cos theta equal to x, and we know cosine function is negative if we consider the principal value case, then angle is in the second quadrant, that is cos of pi minus theta equal to x. From that we get pi minus theta equal to cos inverse x. Therefore, theta equal to pi minus cos inverse x, and finally cos inverse of minus x equal to pi minus cos inverse x. From that I can take the corollary. Sec inverse minus x, that will be equal to pi minus sec inverse x. Pi minus sec inverse x, and in that case mod x is greater than equal to 1. Next, number 3, tan inverse of minus x, that is equal to minus tan inverse x. Here x is any real number, x is any real number, you can prove this similarly. Therefore, I am not showing the proof here. The corollary can be taken as cot inverse of minus x equal to pi minus cot inverse x. And x is any real number. I show the proof here. Let cot inverse of minus x equal to theta. Therefore, minus x equal to cot theta, or x equal to minus cot theta, and this is cot of pi minus theta. Therefore, pi minus theta equal to cot inverse x. Therefore, theta equal to pi minus cot inverse x, and theta already we have taken. Cot inverse of minus x equal to pi minus cot inverse x, and in this case already I have mentioned x is any real number. Thus, Uh, set 8 is discussed. Next, I move to uh, set 9. Sine inverse x is equal to cos inverse root over 1 minus x square, that is equal to tan inverse x by root over 1 minus x square, that is equal to sec inverse 1 by root over 1 minus x square, that is equal to cot inverse root over 1 minus x square by x. And already in the earlier set we have shown cosec inverse x equal to sine inverse 1 by x, and we can say here sine inverse x equal to cosec inverse x. Now let me prove this one. Proof. Let sine inverse x equal to theta. Therefore, sine theta equal to x. Therefore, cosec theta equal to 1 by sine theta, that is equal to 1 by x. From that, theta equal to cosec inverse 1 by x. So this one will be therefore sine inverse x is equal to cosec inverse 1 by x, and from it is clear x non-zero. Then to prove this one, sine inverse x equal to theta, and already we have got sine theta equal to x. Now cos theta is equal to root over 1 minus sine square theta. Therefore, that is equal to 1 minus x square. Therefore, theta equal to cos inverse root over 1 minus x square. Sine inverse x equal to cosec inverse 1 by x. Sine inverse x equal to cos inverse root over 1 minus x square. Then tan theta, that is equal to sine theta by cos theta. Now sine theta is x, and already we have deduced cos theta equal to root over 1 minus x square. From that, theta equal to tan inverse x by 1 minus x square, that is sine inverse x equal to tan inverse x by root over 1 minus x square. Now, following the steps like this, we can easily prove tan inverse this equal to cot inverse, numerator denominator will be exchanged. root over 1 minus x square by x. Also, while we have proved theta equal to cos inverse of root over 1 minus x square, from that sec theta, cos theta equal to this one, therefore we can say easily sec theta equal to 1 by cos theta, that means 1 by root over 1 minus x square, therefore theta, that is equal to sin inverse x equal to sec inverse this. Thus we have proved sin inverse x equal to all of this. Then we can easily prove following similar steps. Cos inverse x is equal to sin inverse root over 1 minus x square is equal to sec inverse 1 by x is equal to tan inverse also we can express in cot inverse form also. Students are suggested to prove yourself. Actually, after learning one set, it will be easier to prove yourself. Then I shall move to the next set. Already I have mentioned we can prove easily following the similar steps. Cos inverse x will be equal to sin inverse root over 1 minus x square, that will be equal to sec inverse of 1 by x, that will be equal to tan inverse numerator root over 1 minus x square, denominator x, that will be equal to, just we exchange the numerator and denominator, that will be equal to cot inverse x by root over 1 minus x square, and that will be equal to cosec inverse 1 by root over 1 minus x square. Then the third one, third part of this set, just I write down, I suggest learner that you shall practice yourself tan inverse x equal to cot inverse x equal to sin inverse x by under square root symbol 1 plus x square, that will be equal to cos inverse 1 by root over 1 plus x square, that will be equal to cosec inverse then sec inverse. Better you practice yourself. First you practice the proof of part 1 of set 9 yourself, as I have solved here. Then you solve other two. Next I shall move to the next set, number 10 set. Sin inverse x plus cos inverse x equal to pi by 2. Tan inverse x plus cot inverse x equal to pi by 2. Number 3, sec inverse x plus cosec inverse x equal to pi by 2. And very important, the domains. Here I mention the domains. Already I have mentioned earlier, x belongs to in case of tan inverse any real number, x any real number. In case of third one, x will be greater than equal to 1 or x will be less than or equal to minus 1. That is represented by, in short, by this one. In set 10, 3 parts are there. I proved 1 and remaining 2 are to be proved by yourself. Let us start by taking sin inverse x equal to theta. Therefore, sin theta equal to x. Now, sin theta can be written as, in terms of cosine, cos of pi by 2 minus theta. Note this one. I have written sine in cosine form. Therefore, as per definition of inverse, this will be pi by 2 minus theta equal to cos inverse x. Therefore, I can write theta plus cos inverse x is equal to pi by 2. And already we have taken sin inverse x equal to theta. Therefore, sin inverse x plus cos inverse x equal to pi by 2. I have proved the first part or number 1 of set 10, and it is suggested that learner students you solve yourself the other two. Already I have repeatedly mentioned that while you are attending these classes, better you take your pen and copy and start working out yourself as I am progressing. That will be better if you follow that way. Next I move to set 11. Inverse y is equal to sine inverse within brackets x into root over 1 minus y square plus y into root over 1 minus x square, 1 minus x square into 1 minus y square. Then tan inverse x plus tan inverse y is equal to tan inverse x plus y 1 minus xy. In this case, xy is less than 1. Now I will show one proof of one or few of these, and the rest are to be proved by yourself. Proof. Let sine inverse x equal to alpha sine inverse y is equal to beta. Therefore, x equal to sine alpha, y equal to sine beta. Therefore, what will be the values of cos alpha and cos beta? Cos alpha, that is equal to root over 1 minus sine square alpha, that will be equal to 1 minus x square, and in case of y equal to sine beta, cos beta will be equal to root over 1 minus y square. Therefore, sine of alpha plus beta, that is trigonometric ratio of compound angle. Already you have used that in class 11. Sine alpha cos beta plus cos alpha sine beta. Now we put these values. X into root over 1 minus y square plus y into root over 1 minus x square. Therefore, alpha plus beta is equal to sine inverse x root over 1 minus y square plus y root over 1 minus x square. That means sine inverse x plus sine inverse y is equal to sine inverse x root over 1 minus y square plus y into root over 1 minus x square. I have proved the first one, and here I take one corollary. Replacing y by x, what we get? Sine inverse x plus sine inverse x. Left hand side will be sine inverse x plus sine inverse y, and on the right hand side, if I put in place of y x, then that will be x root over 1 minus x square into x root over 1 minus x square, that is 2x root over 1 minus x square, or sine inverse x plus sine inverse x means 2 sine inverse x, that is equal to sine inverse 2x into root over 1 minus x square. We can prove this also in different way using the multiple angle formula. What is that? Alternative proof. Let sine inverse x equal to theta, therefore sine theta will be x. Now sine 2 theta equal to 2 sine theta cos theta. Sine theta is x, 2x. Now sine theta equal to x, therefore cos theta will be 1 minus root over 1 minus x square. Therefore 2 theta sine inverse 2x into root over 1 minus x square. Therefore 2 sine inverse x is equal to sine inverse 2x into root over 1 minus x square. Therefore from this one we can prove 2 sine inverse x in this way. Also using multiple angle formula we can prove this. Now another thing, sine inverse x minus sine inverse y, that will be equal to sine inverse within brackets x into root over 1 minus y square minus y into root over 1 minus x square. That is why I like to write in combined form sine inverse plus minus sine inverse y, that is equal to sine inverse within brackets x root over 1 minus y square plus minus root over y into root over 1 minus x square.